All right, recording is rolling. It's Thursday, April 6th. Uh, got a bunch of activities for you guys today related to electromagnetism. You guys remember I told you this yesterday that AP Classroom Unit 7 is open. I've got a due date Wednesday, so we're going to aim for that, right? Okay, so any questions so far? So what's going on? Right, so remember yesterday I was showing you guys some stuff about electricity, circuits. Uh, this is something I really think is critical to know for a number of reasons, because knowing how circuits work, I think I told you guys yesterday, you can understand how traffic flows, how water flows through pipe systems. You can manage systems, think what operations go in a series or parallel, and right, like in order sequentially or simultaneously. Right, so I think this is a really critical skill, even though it's not on the AP exam. So yesterday and today, we're doing some stuff. I'm really condensing like several weeks of material down to 2 days, which better than nothing, I guess, right? Right, so we're going to hit a little bit of this first. Then we're going to construct. I'm going to have you guys construct these items with the materials on your desk, and then we'll move on from there. Right, so let's pick a here. Let's just do a couple of these. Right, I really would like to do more, but really trying to. All right, all right. So what if you have you guys see there's a battery here, right? Battery, and then 3 resistors, maybe like 3 Christmas lights, for example. I was wiring some of these up for you guys yesterday. You guys remember this? These are all in series. So you know they're in series because they're one after another. So the current has to go through one and then the next and then the next sequentially, right? Which means that the total resistance, you just add them up. So you guys see the resistors are 2, 8, and 2 ohms. You guys see that? So it could be like 2 ohms, 8 ohms, and 2 ohms. That means the total resistance is 12 ohms, right? Because it adds up to 12. You guys see that? So the battery, this battery feels like it's pushing against 12 ohms altogether. So next column, what is the voltage drop across each resistor? Now, again, I'm doing this way too fast. I understand that this is not the pace I would normally teach this, but if you're really curious about this, then please go look back at this video, or even you can find my videos that I post for my honors classes and check those out too. But the voltage drop is proportional to each resistor, right? That's what I'm doing. I'm basically going to use this right here. So it's going to go like this. There's 24 volts total. So I have a 24-volt battery here, right? And let's see, 2 out of 12. Guys, 2 out of 12, is that like 1/6? What is 1/6 of 24? 4. So there's a 4-volt drop here. 8 out of 12, that's like 2/3. What's 2/3 of 24? So that's 16. And then 2 out of 12 times 24, again, that's 4 volts. Okay. You guys see how the total voltage drops add up to 24? You guys see that? Right. So if I draw this waterfall model, here, here, try to make this all colored and pretty here. Right. It's like there's a current stream there. Let's drop this down to orange here. Let's go. Here. Let's the screen. Do that. And yellow here. Right. So there's this analogy that I don't know, at least in my mind, helps make make a lot of sense. Right? It's kind of like there's one continuous stream of water, right? And it goes drop, drop, drop. So there's like a 4-volt drop here. There's like an 8-volt drop here, and there's like another 4-volt drop here. Right? You guys can see that. Right. Right. As of 24 volts. 24 volts is battery. Right. 24 volts. Right. All right. Now what's the current? Now here's where we're going to break out Ohm's law, really important formula with circuits. So the voltage divided by the resistance is the current. How much current flows? More voltage, more current. Right? More the battery's pumping, more current. Right? The more the resistance, the less the current. Hey, that makes sense, right? So V over R. Hey, 4 over 2, that's 2 amps. 16 over 8, that's 2 amps. 4 over 2, that's 2 amps. 24 over 12, 2 amps. Right? But it has to be the same number of amps throughout, because look, it's like the same. I mean, there's only one path for the current. So there's a traffic analogy you can use with current. Actually, right. How about this flow rate? So could this be like 2 gallons per minute, 2 gallons per minute, 2 gallons per minute? But it would have to be 2 gallons per minute everywhere, right? Because it's just one stream. Is it? All right, last column here. How many watts? Right now, watts is like a rate of energy. So what's the rate that either the battery is pumping out energy or that each of these is consuming energy? So you can use any one of these. They're all the same. You can substitute Ohm's law into this and derive any of these. I could go current times voltage. I'm going to do that, current times voltage. Right? You could also do either one of these. Right? Sometimes those are easier for different reasons. Current times voltage. 2 amps times 4 volts, that's 8 watts. 16 times 2, that's 32 watts. 2 amps times 4 volts is 8 watts. Okay, guess that? All right, and last one. Now, the last column is, sorry, the last row is from the point of view of the battery. There's 2 amps going through the battery. So the battery is expending 2 amps. Right? It's like kind of like 2 gallons per minute, sort of, just like a pump here, battery. Right? And there's a 24-volt battery. Multiply those together, isn't that like 48 watts? But there's another perspective that would also make sense, which is that electricity supply has to match electricity demand. So the supplied electricity is 48 watts. That's like 48 joules per second. Okay? But look at the demand: 32 here, 8 here, 8 here. That also adds up to 48 watts. Is that okay? Let's do one more, and then we'll be done with this page. Let's do number 4, where they're all in parallel. So all in parallel. Let's say you pump it up to like 24 volts again, and oh look, it's gonna jump down across all the resistors like simultaneously. That means they're all in parallel, right? Which is a different type setup, right? All in parallel. Guys, yeah. Right. So I've got 12 ohms, and 6 ohms, right? And even though they're here, let's put these all in parallel, right? So do you guys remember the analogy I told you, like if you have workers working in parallel on a project, like what if you have a team of guys painting a fence? It would take this guy 12 hours by himself. It would take this guy 12 hours by himself. It would take this guy 6 hours by himself. They make a 3-man team. Do you think they can knock that out in, oh, I'm just going to guess about 4 hours or so? Do you think? Right. So we're going to do this. We're going to do 1 over 12 plus 1 over 12 plus 1 over 6, right? And then take the reciprocal of that. So 1 over the answer. Oh, 3. So the answer is 3. Right? So 3 ohms, the battery feels like it's pushing against. Right? Or if you like the 3-man team, actually it would take them 3 hours to paint that fence. Right? Same math works out. Right? What's the voltage drop? Now in this case, the voltage drop has to be. Do you guys see what the voltage drop is going to be? Somebody tell me while I'm coloring this in. What's the voltage drop across every single one? 24 volts. Yeah, 24 volts. Right? It's kind of like there's 3 side-by-side waterfalls here. Waterfall, waterfall, waterfall. And they're all like 24 like meters high, except in this case, it's gonna be 24 volts, right? Their voltage is kind of like pressure. Like the deeper the dam, the more the pressure, right? So it's 24 volts for every single one of these, right? How much current flows? Well, let's break out Ohm's law. Current is voltage divided by resistance. So 24 volts on 12 ohms, that's 2 amps. 24 volts on 12 ohms, again, is 2 amps. 24 volts on 6 ohms, that is 4 amps. You see that? Now, doesn't it make sense that more current is going to flow through the smaller resistor? If there's less resistance, more current flows that way, right? Finally, through the battery, 24 divided by 3 is 8. Right? Oh, and look at this too. Guys, if there's like 2 gallons per minute here, 2 gallons per minute here, and like 4 gallons per minute here, maybe we should make a big wide waterfall. 2 plus 2 plus 4 is 8. See, we didn't do that for a series because it was just one stream, but for parallel, where it splits and comes back together, you can add those up and they should add up, right? See how it works there? Finally, let's do Joule's law, P equals IV, or that's one version of it. So 2 amps times 24 volts, that's 48 watts. 2 times 24 is 48 watts. 24 times 4, was that 96, I think? Right? 24 times 8, I think it's 192 watts, right? Or here, does electricity supply match electricity demand? So the battery is supplying 192 watts, that's joules per second. And then if you add up each of the power consumed by the resistors, it equates. You guys got two? You guys got? Hey, every good? Right. Again, I know I went through that way too fast, but at least wanted to get you guys some exposure to how circuits work. Right. I would do these other two with you guys, except there's other stuff I want to fit in. When the current splits and comes back together, you got like a combination of parallel and series. It's a little bit trickier, but you have to navigate these rules right here. Okay. Right. Kirchhoff only had really these 2 rules, but these other ones are kind of derivative of that. All right. So let's build some stuff. Let's build some cool stuff. All right, you guys have some materials on your desk. You guys see a long wire with the ends pre-stripped? Right, it's about like 2 desks wide. Right, I guess about a meter long. It's about a meter long. You guys see that? Right. And do you guys see one of these? What do you call this? Like big bolt or something? Right. Here, wind it around, round. Right, wind it around like that, like I have right here. Okay. Right. So while you guys are doing that, let me pull up some. I want to show you guys here. All right, you guys wind that around. All right, so we're going to create an electromagnet. Now, actually, that looks like a lot like an inductor, doesn't it? Right, an inductor will create a magnetic field, right? So got this wind around. Okay. Do you guys see some? Ooh, grab a paper clip. Yeah. You guys got some paper clips on your desk? You guys see those? Right. And you guys see some batteries. You guys see some batteries too, right? Batteries. Right. Now go ahead and do this. Take the two leads of your. Push this all the way to the end. Right. You guys see it pushed all the way to the end right there. Right. 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 Connect the leads of your wire to the battery, like positive and negative. Right. And that should create an electromagnet, which should attract that those paper clips on your desk. Go to the right. Oh, there you go. Look at that. See how it picks up right there? I picked up right there. Boom. Right. And if I disconnect from the battery, boom, it falls down. You see? Right. So that's an electromagnet. It's a temporary magnet. It's a magnet as long as the current's flowing. Look at that. Right there. Right? You guys see that? All right, electromagnet. All right, next thing I'm gonna have you guys put together is a motor. Let me break out some of these posters here. Here we go. So some of the principles today. Here, this is one of the important principles. Right-hand rule. So physical force measured in newtons, a current measured in amps, and magnetic field measured in Tesla. If you have any two of these lying around, the third one can pop up. What we're about to do is, what if you run an electric current past a magnet, right? So electric current, magnetic field. There should be a physical force that would create a motor, right? So let's try that. All right. The way we're going to do that is take one of the shorter ones. There should be one that's about 30 centimeters long. Do you guys see a wire that's about 30 centimeters long? Right. Wrap it around, and there should be some tape on your desk. It looks like this. Right. Wrap it around, tape it. You guys see that? See that? Right. And then take a couple of those paper clips and tape them to a battery like this. Right. You guys see that? Right. Okay, so multiple team members, you guys can help each other out, right? So somebody's making this thing, just wind it around, make it about that big. Right? Somebody tape the, or you could just hold them physically, right? Right. Now, if I hook this to the leads, and the wire has to, the metal has to touch the metal for this to work, right? The insulation part makes the current go around and around, right? But this metal has to touch the paperclip metal, which has to touch the leads of the battery for this to work, right? Now you don't want to leave this on too long. Disconnect this before too long, because otherwise it'll drain the battery, right? But there you go. Now we got like an inductor attached to a battery, right? Then take a stack of magnets, right? So there's a current flowing through this, right? And in fact, that area gives it well, I'm about to give it a flux. This magnetic field, this current, this area, right? Ooh, look at that. And guys, how long will that spin for? Oops, that disconnect. There you go. Yeah, until the battery dies. Well, it was going. What happened there? There it goes. There it goes. Boom. Yeah, that will spin it exactly until the battery dies, because the battery is supplying the energy, right? Yeah. All right. Right. Yeah, you need the magnet to make the motor, right? So the electromagnet, there's no permanent magnet. The electromagnet is just this and the battery. You put this together, and you can like pick up the paperclip. All right. The motor, you needed this loop of wire attached to the battery, so there's a current flowing through it. Hold that over this permanent magnet, and then they'll create a force and it'll cause it to spin. Right. Right. Who's got questions so far? You guys doing all right? You guys doing all right? Right. Next thing I'm gonna have you guys make is a compass. Right. You guys see a couple of cups on your desk? One has a little bit of water in it. You guys see that? Right. Do you guys see how you can put one cup in the other and it'll like float there? It'll float. Right. You guys also have some bar magnets. You guys see those bar magnets? Bar magnets. Right. Right. So you need to know where the poles of these magnets are. The poles are on these faces right here. So here, if I take one of these off, this could be like, this is either the north or the south, and this is the opposite, right? So like this is a pole right here. If I put all these magnets together, then there's one pole here, and there's an opposite pole here, right? You guys got that? Right. So I'm going to put these down so that the poles are faced horizontally, right? Notice I'm not doing so they're faced up vertically, right? Bing, where it's horizontal. See where it's like horizontal, you can see the lines. Okay, see that? And put that down inside this cup, right? And because it's floating, you've just created a compass. Here, show you guys that this does work. Let that go. And it will, if you give this thing a spin, it'll always spin back the same way. Yeah. There's water in the bottom cup, right? The water is not touching the magnets, right? Here, let me close the part. So I got water in the bottom cup. I got the magnets in the dry cup, right? Put this in here, and the magnets will automatically orient north-south, right? If you give it a spin, they'll spin back in place. So no matter how you spin this, it spins back in place. You see that? All right, you guys see that? Who's got questions so far? You guys doing all right? You guys all right? All right, everybody good? All right, you guys ready for the next thing? All right, here, while you guys are trying those out, let me give you guys some pages here. Okay. We're gonna take you guys outside today for an outside activity. We're doing an orienteering activity. Yeah, it is. It is. Orienteering. All right. Nice. All right. So here you go. I gave you guys a treasure map. Out on the practice field, I buried some treasure, and we're gonna go find this. We're gonna go dig it up. So let me show you guys how to read orienteering, and then we'll head outside here in a few minutes. Just gotta show you guys how to read this. Tell you guys about bearing, how to read bearing. So let's get a compass rose going on. So I got north, south, east, west. Right, you guys see that? Right. Let's check out this map. Now, everybody's map, well, there are different versions of this map, but they all lead to the same location, right? Here, guys follow that? Right. So they're different versions of the map floating around, but they all lead to the same location. Reason for that is, as you guys are teaming up and walking around, just you guys kind of like spread out, not all like follow like the exact same set of steps, right? But let's look at what this one says, right? So it says start at the west end field goal post. So out on the practice field, when we head out to the practice field, there's a west end field goal post and an east end field goal post. Okay. I normally do this activity with the compass because the compass can help you navigate. Tell you what though, I found out over time it's really messy to drag all the magnets and water down there, and students don't really like that anyway. So we're just gonna play off the field. We're gonna say this is the west and this is the east, right? Right. And we'll say the field's lined exactly west east, which is pretty close to anyway, right? Right, so you start at the west end field goal post. Right now, there's buried treasure somewhere out on this field. Right, where are you gonna find it? It says walk so many meters, so many degrees east of south. Well, you might have that map, or you might have a slightly different version. East of south. So bearing always starts with the north-south line and then deviates from that. So it's either so many degrees east or west of north, so many degrees east or west of south. Like that could cover everything, right? That could cover any direction. So what does it say? 30 degrees east of south. So start with south, and you go 30 degrees east of that. Do I not have a protractor up here? Well, that's right. I'll just eyeball this. 30 degrees. When you guys are out there, you probably eyeball 30 degrees. Students are usually pretty good at that anyway. Right? Guys, isn't 30 degrees like, well, this whole thing's 90 degrees. So if you cut that into 3, that's about 30 degrees right there, isn't that? Isn't that 30 degrees east and south? Right? Can you walk like that many meters? Right? Now, these are directions. So this is like, do this direction first, then this direction, then this direction. So once you get to that point, then you make your next move. Right? You guys got that? Right. Next one says so many degrees west of south. Right? Now, here's where I would pick up from this point and keep going there. But I'm going to make believe that we're starting at the beginning again just to show you guys relative to the map. So 30 degrees, or sorry, it says 60 degrees west of south. 60 degrees west of south. So again, you start like from of south, and you go 60 degrees west of that. 60 degrees west of south is approximately, boom, that right there. Isn't that like 60 degrees? west of south. You guys see that? West of south, right? And I have another direction that says 45 degrees east of north, right? So again, you're picking up from your last location, but just from this point of view, right? East of north. That's okay. It's like northeast, and it's 45 degrees. So we're talking about pretty much that angle right there. Isn't that angle right there? Does that look like 45 degrees? Right? And that would be east of north. Do you guys see that? Right? Again, students are usually pretty good about this and like almost always find the treasure. Right? And where the treasure is buried, here, I stuck this stake all the way down into the ground where it's like pretty much flush with the top of the grass, but you can just see the very top. Okay? Right. Who's got any question? Any question? Right? And so I'll give you guys points for all those activities we did today. Yeah, all right, so we got enough time. Let's head outside and let's find that buried treasure. There's buried treasure. Yeah.